this presentation, I would like to introduce a novel search algorithm applicable to unstructured P2P networks. First, I introduce P2P networks and will have a quick look at related works. Then I will explain my approach Bacterial Foraging search algorithm and compare the results of applying this algorithm with its rival approaches. To open my speech, I would like to explain how P2P systems work and consider search problem in these networks. In client-server models, a client can upload a file such as a music file, and server stores this file. When other clients look for the file, they first search the server to see if it exists in that server, and then download it directly from the server. However, in P2P networks, the system has omitted the central server, and therefore the peers are directly connected. To find a file, each peer can send its request to its peers and download the file directly from them. In unstructured P2P networks, peers are free to share any file and might be connected to any other peer, so there is no correlation between files and their location. So, how do you know where your desired file is in such a big network? Different search algorithms have been proposed so far, and their aim is to maximize the probability of finding the requested file, or in other words, increase the success rate. The more resources a query finds, the better the requester can download the file. In addition, search time should be as short as possible, and the number of transmitted messages to find the file shouldn't be high. However, to implement a powerful search algorithm, we should also consider the quality of discovered sources, as it directly influences download quality. If a search algorithm finds sources with higher upload bandwidth, it can help to network load balancing and increase user satisfaction. Bacterial foraging search is designed to find sources with higher upload bandwidth without imposing any changes on network graph or file distribution. This algorithm is inspired from the behavior of E. coli bacterium when it looks for food. We have categorized the so far proposed algorithms to three main categories. Blind search algorithms, which never consider network conditions for their operation. Informed search algorithms, which use whether predefined information of the network or try to learn more about the network and adapt the search according to that information. The third group impose rules on network graph or replication to get the best result. Bacterial foraging search algorithm is an informed search algorithm which uses predefined tables for its routing decision makings. First, I explain the biology of bacterial foraging search for food. E. coli bacterium, which swims in a straight line or can tumble around to find a new direction for its next swim, tries to go toward the food source by sensing the environment and climbing up the nutrient gradient. Just like this behavior, our algorithm is designed to lead search agents to source nodes with higher upload bandwidth and longer presence time in the network. To do so, stronger nodes let more neighbors know about their contents, and therefore the probability of finding a strong node is increased. We consider a two-layer genutella-like structure in which leaf nodes are connected to superpairs. These leaf nodes calculate their accessibility value G and announce this value and their shared contents to the supernode. This G is a function of upload bandwidth and estimated presence time of the leaf pair in the network. The superpair gathers all indices of files and accessibility values and saves it as its source table. This source table is advertised to immediate supernode, and the receiving supernode multiplies the received advertised table to its processing capacity and stores the new value in its path table. Then the advertised table continues its way to next layer of neighbors until the values in that table become negligible. Finally, all the nodes create their path tables and the environment is ready to release the search agent. In the second stage, the search agent begins looking for its desired file. For example, node E is looking for file F5. It sends the request to node D. The request message checks if node D has any trace of F5. As it understands that D is in the path of the source of F5, the bacterium continues its way to nodes C, B, and finally A as the source of F5. In the second example, D is looking for file F3. D sends search agents to its neighbors E and C. The search bacterium knows that in node D, the access value was 2.5. Therefore, it knows that if the access value in the next node is increased, it is on the right path to the source of F3. Node E, which has a smaller value than D, eliminates the search agent, and therefore searching is cut in the right direction. To simulate the performance of this algorithm, we considered a two-layer genutella-like structure and assumed that the number of supernodes to be 10,000, and each supernode is connected to 10 other supernodes. Therefore, we can advertise the source tables to at most 3 layers of neighbors. We have assumed that 10% of nodes are strong, 50% are medium, and 40% are weak nodes. If we assume that all users have a download speed of 3 MB per second, and each user can download from 3 peers simultaneously, we compare our algorithm, jumping bacterial foraging search, with 4 other rivals: dynamic search, local index search, adaptive probabilistic search, and ant colony optimization search. In a static environment, the success rate of JBFS is obviously higher than other investigative algorithms. Comparing download time and the imposed load of these algorithms, we understand that JBFS has the shortest download time while its load is acceptable. To study load balancing, we selected a particular node which was looking for a particular file. Therefore, our comparison is absolutely fair. We see that for rare files, JBFS has the highest success rate, and it finds more strong nodes than other algorithms. In a dynamic environment in which files and nodes join and leave the network continuously, Updating the path tables costs additional load. As shown in this figure, informed search algorithms lose their validity by time in dynamic environments. However, in a dynamic network, JBFS still has the shortest download time, although it imposes a large load to the network because of updating tables. In summary, we have introduced a new search algorithm inspired by Bacterial, Foraging for food. This algorithm obviously has increased the success rate of the search, decreased the download time, and enhanced network load balancing, as it can find stronger nodes with a higher probability. Thank you very much.